Now let's talk a bit about what the right way to interpret resonance is. Well, we've drawn one picture of acetate here. Here's a Lewis structure for acetate, and here's another Lewis structure for acetate. But which of them is the correct or valid Lewis structure? Well, they're both correct. They're both valid. That's what resonance means. Resonance is when there's more than one valid Lewis structure that you can draw for a compound. Now, it's easy to misinterpret resonance, partly because in some ways the symbols and the notation we're using are misleading. So how are these symbols somewhat misleading? It's important to keep in mind that even though this is the correct symbol for resonance, it's a little bit misleading, because this symbol makes it seem like the acetate is constantly flipping back and forth between these two pictures. This is misleading because it makes it seem like the acetate sometimes looks like this and sometimes looks like this. Well, that's not the correct interpretation of resonance. The acetate is not shifting back and forth between two different pictures. The acetate just looks like one thing. But what the acetate looks like is something we can't draw. There's no way to accurately draw a correct picture of what the acetate looks like. Instead, all we can do is draw a bunch of resonance structures, and then we have to say that the true picture of acetate is a kind of blend or average of all the different resonance structures that we've drawn. So again, we're not saying that the acetate is flipping back and forth between these two pictures. Instead, we can't draw what the acetate really looks like, but we can say that it's a kind of blend or average of these two pictures. Well, what do I mean by a blend or an average? Well, notice that in this picture, the oxygen has a negative formal charge, and in this picture, this oxygen has 0 formal charge. So how much formal charge does the oxygen really have? Well, it has a charge that's kind of an average of these two pictures. So essentially, this oxygen basically has a 1/2 formal charge. In this picture, it has a negative formal charge and a -1 formal charge, and here it has a 0 formal charge. Well, the average of those two things would be a 1/2 formal charge. And for by the same token, this oxygen also really has a 1/2 formal charge. It has a 0 formal charge in this picture and a negative formal charge in this picture. Well, the average of those two things would be a 1/2 formal charge. There isn't really any great way to draw an oxygen with a 1/2 formal charge, so the best that we can do is draw two pictures and say that the true picture is a kind of average of those. We can also look at that for the bonds. So I hope you're familiar with the idea that double bonds are stronger than single bonds. You should know that double bonds are stronger than single bonds. Well then, how strong is the bond between the carbon and the oxygen? Well, in this picture, we drew it as a single bond. And in this picture, we drew it as a double bond. But remember, that does not mean that it's flipping back and forth between being a single bond and a double bond. There's just one type of bond between the carbon and the oxygen, but we can't actually draw what that bond looks like. All that we can say is that it's kind of blend or average of a single bond and a double bond. So how strong is this bond between the carbon and the oxygen? Well, it's stronger than a single bond and weaker than a double bond. The bond between the carbon and the oxygen is going to be stronger than a single bond and weaker than a double bond, because the actual character of the bond is a kind of average of this picture, where it's a single bond, and this picture, where it's a double bond. And we could say the same thing for this carbon-oxygen bond as well. That is, the strength of this bond is between the strength of a single bond and the strength of a double bond. All right, so again, make sure that you don't think in your mind that we are moving from one picture to the other. Instead, there is really only one way that the molecule looks, but we can't actually draw that way. For example, we can't really draw a bond that's midway between a single and a double bond. All we can do is draw one resonance structure with a single bond and one resonance structure with a double bond. And then we kind of imagine in our head somehow a bond that's a blend or an average of a single and a double bond. These electron-pushing arrows are a very useful tool, but again, they can be kind of misleading, because when we talk about the electron-pushing arrows, we talk as if the electrons were actually moving. For example, here I might have said that we're moving this lone pair into the pi bond, and we're moving this pi bond into a lone pair. But that's all just a figure of speech. That's just a kind of bookkeeping to make sure that we're drawing the correct resonance structures. Remember that in reality, the electrons are not moving from the lone pair to the double bond. Instead, in reality, the electrons are just spread over the molecule in certain ways. But the way that the molecules are spread over the molecule, the way that the electrons are spread over the molecule cannot really be drawn in a Lewis structure. So instead, we draw a bunch of different pictures and say that the true molecule is a blend of those. All right, so to repeat that, when we are using electron pushing arrows to draw resonance structures, a lot of the time we talk as if the electrons were actually moving from one place to another. That's all just a figure of speech. That's just a trick or a tool to help us draw the resonance structures correctly. In reality, we're not actually moving from this picture to this picture. Maybe a couple of analogies would help here. One analogy that I've seen used is of mules. Do you know what a mule is? The mule is the offspring of a donkey and a horse. So if a donkey and a horse mate and have offspring, the offspring is not a donkey or a horse, it's known as a mule. So we could kind of think of a mule as a kind of resonance structure of a donkey and a horse. What do I mean by that? Well, imagine that you were talking to somebody who'd never seen a mule before. They'd never seen a mule, but they'd seen lots of donkeys and they'd seen lots of horses. So how could you describe to them what the characteristics of a mule are? Well, you could say, well, a mule is a kind of resonance structure of a donkey and a horse. What does that mean? It means that the characteristics of a mule are kind of a blend or an average of the characteristics of a donkey and a horse. So if you can form a picture in your mind of a donkey and a picture in your mind of a horse, and if you can kind of blend those pictures together, that'll give you a somewhat accurate idea of what a mule is like. Now, the really good thing about this analogy is that it forces you to see that resonance does not mean that we're flipping back and forth between the resonance structures. So, for example, we would not want to say that sometimes the mule looks like a donkey and sometimes it looks like a horse. It's not flipping back and forth between these two things. There's only one thing that the mule looks like. But if someone had never seen a mule before, they wouldn't have a mental picture of that. So the best they could do would be to form a mental picture of a donkey and a mental picture of a horse and blend those together in their minds. But again, even though we have this double-headed arrow here, we're not, when we talk about resonance, we're not really suggesting that the mule is flipping back and forth between these two appearances. It only has one appearance. So hopefully that analogy helps you a little bit to understand what resonance means. Another analogy that might help us to understand resonance is to think of a nectarine. Suppose that you're talking to somebody who's never seen a nectarine before. How could you give them a mental picture of what a nectarine is like? Well, let's say that even though they haven't encountered nectarines, let's say they have encountered peaches. And they have encountered plums. Well, you might say that a nectarine is a resonance structure of a peach and a plum, because the characteristics of a nectarine are in some way a kind of blend or average of the characteristics of a peach and a plum. For example, a nectarine is smooth like a plum, so it gets that characteristic of a plum. On the other hand, a nectarine kind of tastes like a peach. So the overall characteristics of a nectarine are a kind of blend or average of the characteristics of a peach and the characteristics of a plum. Now again, hopefully this helps us to see that resonance does not mean that we're flipping back and forth between the two structures. It's not true that sometimes a nectarine looks like this and sometimes it looks like this. A nectarine always looks like one thing. But if you've never seen a nectarine before, you wouldn't be able to form a direct mental picture of that. Instead, maybe the best that you could do would be to form one mental picture of a peach and a separate mental picture of a plum, and then kind of blend or average those together in your mind. So that's the idea of resonance. When we can't draw a single picture that captures what something is like, we can draw a bunch of different pictures and blend them or average them together in our minds. That's what resonance means. So these are some good analogies for resonance. So you can see a bad analogy for resonance would be Superman and Clark Kent. Because sometimes Superman looks like Superman, and sometimes he looks like Clark Kent. He's always switching back and forth between Superman and Clark Kent. Well, that would not be resonance. That's not resonance. Resonance is not when you're shifting back and forth between different appearances. Again, resonance is when you have only one appearance that is difficult for us to describe. So we describe it by giving a bunch of separate pictures and ask you to blend or average those together in your mind.